Welcome back, everybody, to the next video. Today, we're going to be talking about fiber products. So recall that given a diagram of sets consisting of maps alpha from A to C and beta from B to C, the fiber product A cross B over C is the subset of the product A cross B consisting of pairs alpha A, B such that alpha of A equals beta of B. The fiber product carries the obvious projection maps to A and B, commuting this C square, so the square that I have drawn here. This is an example of a Cartesian diagram, which is just some square, E to B to A, and then maps alpha from A to C, beta from B to C, such that the projection maps, if you like to call them that, from E to A and E to B, identify E as the fiber product, A cross B over C. Okay, so we can think about this a little bit more categorically. We can think about this functor theoretically. So given maps of set-valued covariant functors, so natural transformations on a category C, let's say alpha from A bar to C bar and beta from B bar to C bar, we can actually talk about the fiber product of these functors. So A bar cross B bar over C bar. Well, this is a functor, so what should its value on an object X of C be? It should be what you think it is, A bar of X cross B bar of X over C bar of X. And this, yes, this does complete a Cartesian square of functors. So there's a naturality to check there, but that just follows from everything being functors. Okay, existence. So even if A bar, B bar, and C bar are representable covariant functors on C with representing objects, let's say A, B, and C, the fiber product A bar cross B bar over C bar doesn't actually have to be representable in C. But if it is, its representing object, which we will call A cross B over C, coming with a pair of morphisms from itself to A and B, is well defined, and it's unique up to unique isomorphism in C by the usual category theory nonsense. When this happens, we say that the fiber product A cross B over C exists in the category C. And like I just said above, we actually get a Cartesian diagram from its representing object, A cross B over C, to the representing objects B and A of the original functors over C, the representing object of kind of the base functor C bar. Okay, fiber products do exist in the category of sets, in the category of commutative rings, less obviously in the category of schemes over a base scheme S. That's covered in Bakil's book or Hartshorn or wherever you like. And plenty of other categories have fiber products as well. Okay, when fiber products exist, we can use their Cartesian diagrams of functors to provide a necessary condition for representability. Let's do that. So suppose we have a covariant set valued functor F on a category C, so something like this. If you apply F to the A cross B over C diagram, you get by functoriality and naturality, F of A cross B over C, map from there to F of B and F of A, and then maps from F of B and F of A to F of C, which we'll also call alpha and beta. This is by the covariance of the functor. Okay, if F were representable with representing object, let's say X and C, this would be a Cartesian diagram by the general remarks we just made, right? But what's another way of saying that? Another way of saying that is that the natural map H from F of A cross B over C to F of A cross F of B over F of C is a bijection, okay? And so, to summarize, it must be the case that for a functor F to be representable, this H map is a bijection for all Cartesian diagrams A cross B over C in the category C. And so we'll name this property. It's called the Mayer-Bitoris property. So how about the categories we've been working with over the last couple of videos? Well, let's let A be a coefficient lambda algebra. It turns out that fiber products do exist in that full subcategory C sub lambda of A. That is another way of saying that, just unwinding definitions. If we have maps of Artinian coefficient lambda algebras A to C and A to B with A augmentations, then the subring A cross B over C is again an Artinian coefficient lambda algebra with A augmentation, because that's what this category is. And this is the categorical fiber product. So I told you one reason last video or two videos ago, I can't remember. One reason for using this full subcategory is just easier to work with Artinian objects because you can recover kind of objects in the full category by taking inverse limits. But this video gives you another reason that you might want to work with this full subcategory C sub lambda of A rather than C hat sub lambda of A. So dropping the Artinian adjective. And the reason for that is it turns out that C hat sub lambda of A is not closed under fiber products for a subtle reason. The fiber product of elements in that category need not be Noetherian. And Noetherian was one of the conditions it took to be in this category. You can see Cornell, Silverman, Stevens, page 270 for more details. Okay, so we'll look more into this representability stuff next video. Thanks for watching, and I'll see you then.